This video will show that line integrals depend, in general, on path. We have two types of paths, broadly speaking. We have open paths, where you start at one point and you go to another point. You also have closed paths, where you start at one point and the point that you end at is the same point that you started at. In general, whether we go from here to here or from here to here will give us a different line integral, and that's what we're going to show in this video. In the previous video, we went along 1 to 2 to 3 and showed that the work done was minus 38. We're going to take a different path now. We're going to go 4, 5 over to that same point 2, 2. So we're going to break that up, our line integral, because in general, our work is equal to the line integral of force, dotted with the L, from A to B. But in this case, since we're going along path 4, we're going to go from 0, 0 up to 0, 2. And then from 0, 2, we're going to then go over to 2, 2. Now for this first part, path 4, we're going straight up. So this means that our dl is going to equal dy y hat. So when we do our entire line integral, work is going to equal force 0, 0 up to 0, 2 of 3, oops, let's make that more clearly a 3x squared y x hat plus 2y squared, oops, 2y squared y hat. And because we're along this particular path, we're going straight up, this is going to be dotted with dy y hat. And this dot is just a normal dot product, so that means we're going to take this part and we're just left with the integral from 0, 0 up to 0, 2 of 2y squared dy, which is, of course, oh, pardon me, it's just a 2y, not 2y squared. And we're left with y squared, evaluated from 0 to 2, which of course will give us 4. Now we're going to go from 0, 2 out to 2, 2. So we're going to add these two things together. So plus the integral from 0, 2 up to 2, 2. And once again, we have 3x squared y x hat plus 2y y hat dotted with, and now since we're going along horizontally, our dl is going to be different. It's going to be dx x hat. Now, all along that horizontal line segment, y is equal to 2. So we've got 3 times 2 times x squared, and the dot product is just going to give us dx, and we're integrating from x equals 0 to x equals 2. So this winds up being 2x cubed evaluated from 0 to 2, which is, of course, 16. So 4 plus 16 equals 20. We've already seen that if we go along this path, it's minus 38, and if we go along this path, it's 20. So we've already seen that it's different. But let's take one more path, going straight from 0, 0 up to the point 2, 2, along the line y equals x. So we have the line y equals x, which further means that dy equals dx, and that means that dl is going to equal dx x hat plus what would normally be dy y hat can actually be written as dx y hat. When we make this simplification, this also means that our limits of integration, instead of being 0, 2 to 2, 2, is just going to be 0 up to 2, because we know at every point x equals y. So that means we're going to integrate from 0 to 2, and we're going to say it's 3x squared x hat plus 2x y hat. And then this is going to be dotted with dx x hat plus dy y hat. Oh, except that dx equals dy, so we can replace this with a dx. Well, what does this give us? As we combine our terms, this term is going to combine with this dx, and this term is going to combine with this dx, and of course 3x squared x is 3x cubed, so this is going to give us the integral from 0 to 2 of 3x cubed plus 2x, and all of that is going to be dx. And then we integrate as we always do. This becomes 3x to the 4th divided by 4 plus x squared. And this is going to be evaluated from x equals 0 up to x equals 2. So we put in 2 here, divide by 4, so that's going to give us 12 plus 4 minus 0 is equal to 16. What this video showed is that if we take one path for our line integral, we can get negative 38. If we take a different path for our line integral, we can get 20. And if we take the most direct path for this particular line integral, we wind up getting 16. Clearly, taking a line integral depends on the path that you take in general.